antiferromagnetism of these materials. Now, if we calculate Fermi energy for these elements, 3D, 4D, and 5D, this graph looks like this. So Fermi energy is in statistical mechanics is a chemical potential, and this chemical potential corresponds to the quantity of energy that's required to add one electron to the system. And for this case, for 5D, is this value of Fermi energy or chemical potential is larger compared to other 3D and 4D elements. Now, this is what I said before. This is bandwidth versus atomic number. This atomic number corresponds to number of d electrons here, and for 5D, this bandwidth is larger compared to all others, and 3D is just in the middle, and this 3D 3D bandwidth corresponds also to larger value, to better magnetism for for these 3D elements. So bandwidth increases with increasing the period, 5D, and then 4D and 3D. Now, for low energetic outer shells, we have more localization, and inside each series, the bandwidth decreases with the atomic number. So, for example, if you look inside of this series, inside of this bandwidth, we have decrease of atomic number here. Now, let's look to the itinerant magnetism. So, if we have, for example, we can have two kinds of electrons in the magnetic materials. If these electrons are located in the atom, they are called localized electrons. In some cases, these electrons can go outside to the lattice, and they become free electrons in this case. So we already saw in this case for the transition metals, when, for example, we have iron, have 2+ or 3+ structure in this case. Correspondingly, this iron has given to the lattice 2 electrons or 3 electrons. Now, if you consider here this magnetism in these so-called itinerant magnets, so the itinerant magnets correspond to the materials magnetism in which we consider as those due to the free electrons here. Now let's consider here a hypothetical metal. If we here this red line, red half circle corresponds to the density of states versus energy for spin up electrons, and the blue corresponds to spin down electrons. Now let's consider the case one, for example, this density of states will be asymmetrical. Then in this case we have here this picture. So for the blue, we have larger value of density of states compared to the red ones. Now kinetic energy has this formula. In this case, since we have spin up and spin down electrons, we can write down here the number of states using this sum of this number of states for spin up and spin down electrons. And the kinetic energy is just written like in this line. And Coulomb repulsion is just energy between electrical energy of interaction between two electrons here. So this Coulomb repulsion is written with this form here. Now here is this O is Coulomb interaction, and it just depends on the energy overlap, integral overlap. So if we look upon splitting the density of states, let's consider that this they have splitting of energy, and this splitting of energy is equal to delta E. Now in this case, if we calculate energy change for kinetic energy and potential energy, these changes will be looking like this. Now total change of energy will be just sum of these two energy changes, and this written is here. Now we can see that in parentheses here, in square parentheses, it has this expression here 1 minus O n EF. N EF is just the number of states at Fermi energy. So for if delta E is less than 0, in this case it favors this structure, and this corresponds to the stable structure. And in this case, this expression in square brackets should be less than 0, and this is criterion for band magnet. So in this case, U times number of states at Fermi energy has to be larger than 1. So let us consider this for this 3D, 4D, and 5D elements here. Now, in 3D elements here we have here Stoner exchange. So Stoner exchange corresponds to this U value over there in the previous slide, and this corresponds to this 3D elements dependence on number of d electrons here. For 4D electrons, it looks like this, and 5D is here. So 4D and 5D just they follow same pattern, whereas in the case of 3D elements, we have a very large increase up to nickel atom, and then sudden decrease from nickel to copper. Now, if we write down here second graph, if you look at the second graph, and in second graph we have here this on y-axis Stoner criterion. The Stoner criterion is just this number of states at Fermi energy times this U, this Stoner exchange, so value of the interval. So for this case, for 3D elements, we have only 1, 2, 3. This corresponds to iron, and then cobalt and nickel. So these 3 elements have show the values of Stoner criterion larger than 1, and they they show better values of this delta E. So smaller values of delta E, and this favors this itinerant magnetism here. And we have also knowledge of this titanium, vanadium, chromium, manganese being good magnetics. So we conclude from here that this magnetism in these materials favors this intrinsic magnetism. So magnetism that's originates from the magnetism of the electrons on the atoms or atoms. Now, if you look at the third here graph, we can see that spin-orbit coupling here is written here on the y-axis, and again the 3D, 4D, and 5D elements on the x-axis here. And for 5D elements, we have larger values of spin-orbit coupling. We will soon see that these elements of 5D electrons, and if they have spin-orbit coupling larger than electron-electron interaction, this corresponds to the JJ coupling, and these 5D elements will be favorable for Josephson junction elements, and also elements that are built on Zelensky-Moria effect. So these effects we will soon see in the next our lectures.